Hello, I want to talk today about numerical methods for integration. What do I mean by numerical methods? I mean, it's an integral that maybe you can't evaluate directly, you can't get an exact value for it. So you just want an approximation. You want some good number that estimates the value of the integral. Now, one sort of nice geometric way to do it is as sums of trapezoids, and this is called sometimes you'll see this called trapezoidal rule. This is a commonly used method. So you say, picture it as if you were about to do a Riemann sum, but instead of just going straight across the top and doing a rectangle, let's instead do trapezoids, because maybe, the tops of trapezoids, they're allowed to tilt, right? So we're saying that shapes like this might better estimate the area under our graph instead of shapes like this, right? That's the idea of the trapezoidal rule. Now, or you could, and I should say approximate, because we're just doing finitely many trapezoids, right? You could also say, how about sums of areas under parabolas? You could do that. This is another popular one, because you could say, hey, trapezoids, they don't curve. Maybe I could do little arcs of parabolas along the tops there, right? So maybe instead I do figures that look like this, right? I have a little arc of a parabola up top, and then it looks like a rectangle then below that, and maybe I could calculate those areas. That's another popular one. This is called Simpson's rule. Sometimes you'll see that as a way to get a numerical approximation for an integral. These, I have the word classical written up here. These are very traditional in a lot of calculus curriculums. I do not want to talk about these today, but instead I just want you to be aware that they're out there, and I want to instead show what's probably a more modern approach, right? So a more modern approach, often this is called Monte Carlo, after the great gambling city. Not trying to not saying that you should immediately take up that vice. I mean, great in the sense of gigantic, right? The big gambling city. So Monte Carlo is the name of this approach, which it's called Monte Carlo because it, like gambling, it has an element of chance to it, right? It has a more randomized approach. So here's the idea for Monte Carlo. It relies on one key fact. If you have an area, let's say you have a rectangle, and let's say there's a region inside this rectangle. And it doesn't really matter what this region is. It could be any strange shape at all. So say you have some region R inside this rectangle, right? And let's say that rectangle is W by L, right? Let's say that's your rectangle. So what would happen if you think about throwing darts, randomly selected points? So let's select in points at random inside the rectangle. Right, so we get, there's a point, 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 point. And maybe some of them land really close to each other. Maybe some of them are more spread out and don't have any points nearby, right? Let's select in points at random inside the rectangle. Then you could say, okay, how many would you expect to lie inside R, inside that region R, right? Well, think about the areas. How much of this rectangle is occupied by R? Well, so you'd expect out of the n points, you'd expect n times what? The area of R divided by W times L, the area of the rectangle, right? Think of that ratio of areas, area of the gray region versus the area of the box. Think of that as say a percent. you can say whatever, say that region R occupies 40% of the box, then with randomly chosen points, you would expect 40% of the randomly chosen points to lie inside R, right? So that is that's a key idea here, right? So this would be the number of points lying inside R, right? That's a nice, that's what you would expect. You'd expect the number of points lying inside R to be what I wrote down here. The total number of points times the ratio of the areas. Well, why does this give us a way to calculate integrals? Well, here is what you can do then. This gives you a way to estimate an area. Remember, integral represents area, right? So if you just multiply the W times L over to the other side and divide by N, what do you get? You get an estimate, right? The area of R should be roughly what? It should be the number of points inside R divided by N times the area of the rectangle, WL, right? I multiplied over the WL and I divided by N. So that's a way to approximate the area of a region, right? So now I could, now I can actually do this to calculate integrals or to estimate integrals, right? It won't be perfect. The hope is as N goes to infinity, this quantity would converge to the true area, right? But you get into lots of sticky details about how you're implementing your algorithm, what does random mean, how are these points being chosen. So there's a lot to think about, but this is the key idea of a Monte Carlo integration problem. So let's say, for example, let's say that 40 points out of, sorry, let's say this. Let's say 100 points are chosen at random in the rectangle with vertices 0, 0, 4, 2, 4, 0, and 0, 2. And let's say of those, of the 100, right, we'll say 40 lie below the graph y equals root x, right? Let's use this experiment or this sample, right, to estimate an integral, right? To estimate this integral. The integral as x goes from 0 to 4 of the square root of x dx. So this is a Monte Carlo example. So what we're saying is we have this rectangle, right? We have our x and y axis. We have these points, 0, 0, right? 0, 2, 4, 0, and 4, 2. So this is my box, right? And then I have this graph, y equals root x. Right? And then we have this region R, and R is the region that's below y equals root x. So then what would we have here? By this experiment, we would say, okay, the area of R, which that's what this equals, right? This, by definition of an integral, this equals the area of R, is estimated to be what? Well, it would be 40 out of 100, right? When we did our 100 points at random, 40 of them landed under the graph y equals root x, right? So I had 40 points down here. I had 60 points out here, right? For my 100 total. So 40 out of 100 That's how many points landed under R. So I would guess that this, if we multiply it by the area of the rectangle, that should give us an estimate of the area of R, right? So this is saying take 40% times what? What's the area of the rectangle? This is a 4x2 rectangle, right? So 40% of 8. So this would give me 3.2, right, as my area estimate. Right, so that would give us an estimate for the value of this integral. Now you could probably see this is only an estimate, right? Clearly 3.2 is not the correct answer, right? Because this region R takes up more. You can imagine drawing a line that splits the rectangle into two triangles. Clearly this region R takes up more than half of the rectangle, right? Here in this data set, we got very unlucky. This is why, some people don't like Monte Carlo algorithms and instead would prefer to do something like trapezoids or parabolas, right? Simpson's rule, trapezoidal's rule. But here's the thing, just keep taking more points, right? If you, in practice, if you've coded up a Python script or something to do this for you, we'll let the number of points go up and up and up and up. And instead of getting we got an approximation here that was not very accurate. As the number of points goes up, you could basically guarantee that the unless there's something very strange or very specific going on, that the estimates that you get as the number of points increases will become more and more accurate. Right? So there we go. That's how Monte Carlo approximation works, right? For integration, right? This is our rather than the classical methods, which were popular at one point. This is sort of the more modern way to look at a calculation like this is really with the Monte Carlo approach. So, great. Thank you.